Hello and welcome to section 5.2. We're going to be talking about chirality in this section and looking a little more at specific types, a specific type of superimpose or of stereoisomer, which are called chiral molecules. Now, chiral is a word that comes from the Greek meaning hand, or the Greek word that means hand, and it is something that chiral molecules are things that we interact with often in our daily lives. Take, for instance, your hands. Your hands are non superimposable images, which means that if you were to hold them up to each other, like if you were about to clap, you would notice that your hands um, mirror each other. Your thumbs are in the same place, more or less, across the mirror, as are the rest of your fingers. But if you were to put the backs of your hands together, you would see that they are mirrors. However, if you were to line up the fronts and backs of your hands, so let's say take the front of your right hand and put it on your left, you would notice that they do not superimpose on each other, or you can't you can't put your one hand on the other um, in the same orientation and get it to be the same molecule. That's why it's called a chiral molecule. If instead you took a pencil or a computer and you stacked one on top of the other, those are superimposable because they would completely look identical from a vertical view. Similarly, molecules can be chiral. So if you were to take a molecule like this one on a wedge, let's say it's a OH. Um, this one over here is a CH3. Here, this is a ethyl group. And you put a mirror plane right in front of it. So assume that this molecule walk up to a mirror. You could make the same molecule that is its mirror image, right? Just like we were talking about with our hands. But just like with our hands, we could see that the molecule I just drew on the right is not superimposable with the molecule that we had on the left, correct? You could imagine that if you were to put the OH, you were to rotate the molecule so the OH on the wedge is in the same place as the OH on the wedge in the original molecule, then on the left, in the plane bond, you would have that ethyl group. And so that would mean this molecule is not the same molecule, meaning that the one on the right is non superimposable with the one on the left. That makes both of these chiral molecules. Moreover, it makes the carbon that is attached to the four unique substituents, it makes those carbons chiral carbons. And chiral carbons is the name that we give to carbon atoms that have four distinct substituents on them. And that's what makes them chiral specifically. We talked about how these are pairs of molecules, right? These are mirror images of each other. And in fact, that is a special definition of a type of stereoisomer and a type of chiral carbon that we can come into contact with. Enantiomers. That's the name for non superimposable mirror image molecules, which is what we drew here. They are mirror images because if you look across the mirror plane, as we just drew, they are the same, but they are non-superimposable with each other. And you can talk about enantiomers either as a pair together, like we did, or as a single enantiomer in a pair. Both are fine. So one thing that we're going to have to be able to do in this course, in this chapter, that's very important is we're going to have to be able to identify when in a molecule you see a chiral carbon. So if I were to draw this molecule for you, hopefully you can identify how many chiral carbons are present, which is one. One chiral carbon, this one, and it's chiral because there's an H on a dash that we don't see. Remember, in bond line structures, which includes wedge and dash bond line structures, we don't draw the hydrogens. So, or we don't draw the hydrogens that are bonded to carbons. So often you could see that the you need to be able to place the hydrogens where they go, and that means even if they're not shown. Another type of a molecule, chiral molecule, that we deal with in our lives that maybe we don't even realize are those of amino acids. And amino acids often will have, they can have lots of structures. I believe there are, what are there, 20 natural amino acids, something like this, where each of these are used to make proteins and enzymes in our bodies. And here we're going to learn about a special way to draw structures, which is that of a variable substituent. Here, they're called variable substituents because the R can mean anything. It can mean a methyl group for alanine. It can mean an isopropyl group for isoleucine. Perhaps it can mean, what is that? It's a methyl OH for threonine, I think. I don't remember. I get serine and threonine mixed up. Anyway, each of the amino acids are all chiral molecules as well, with a chiral carbon in the middle here. And remember, it's chiral because of the hydrogen that we are not seeing. So just a couple more examples. If we were to draw, let's do that better. There we are. If we were to draw this molecule, could you name all of the chiral carbons here, or could you point them out? I'll give you a second to do that. You can even pause if you need to. The chiral carbons are here and here, right? There are 4 substituents on both of these because each has a hydrogen that we're not showing. And in blue, I'm going to circle each 4 substituents. So for the top one, the 4 are these, right? And for the bottom carbon, the 4 substituents are these. So you're going to need to be able to identify how many chiral carbons are present in a molecule for probably the rest of this course, I would bet, and the rest of organic chemistry in general too. So this has been section 5.2.